In section 1.4, we're going to look at quadratic equations. A quadratic equation in the variable x is an equation that can be written in standard form ax squared plus bx plus c is equal to 0, where a, b, and c are real numbers and a is different from 0. We want the a term to be non-zero so that we do have an x squared term here. Typically in standard form, what that means is we have all of the variables on the left-hand side written in terms of decreasing powers of x and 0 on the right-hand side. A simple example of this would be x squared minus 7x plus 10 equals to 0. This is a quadratic equation in standard form. The coefficient a, which is the coefficient of x squared, is 1. B would be negative 7, and c would be equal to positive 10. The easiest way to solve a quadratic equation when possible is to invoke what's called the zero product principle. We notice that x squared minus 7x plus 10, this quadratic expression actually factors. It factors as x minus 5 times x minus 2 equals to 0. And what we have right now is something that's very special. We have a product. We have something times something equals to 0. And the zero product principle of the real number says the following. If we have a product that is equal to 0, then one of the two factors, at least one of the two factors themselves, must be equal to 0. Meaning that either a has to equal to 0 or b has to be equal to 0. To solve the quadratic equation above, once we have it factored and set equal to 0, then we can simply set each factor equal to 0 individually because of the zero product principle. This means that either the x minus 5 factor equals to 0 or the x minus 2 factor equals to 0. And now each one of these is just a basic linear equation where we can go ahead and solve for x. To solve this one for x, you just add 5 to both sides, and we see that one solution is x equals to 5. And for this one, we simply add 2 to both sides, and we get the solution x equals to positive 2. So steps for solving a quadratic equation by factoring. So first thing we want to do is write it in standard form. Move all of your terms to the left-hand side, get 0 on the right-hand side, or at least on one side. Write it in standard form, ax squared plus bx plus c. The next thing we want to try to do is factor the left-hand side, which is not always possible, but if you're able to, that's what we want to do. And then once you have it factored, simply go ahead and set each factor equal to 0 individually. Okay. Let's take a look at the first one. In example 1, we want to solve 4x squared minus 2x equals to 0. This is a quadratic because we have the x squared term here, and it's the highest power of x. Notice that it's already in standard form. We have one side 0, and our left-hand side is in decreasing powers of x. The next step to solve by factoring would be to try to factor this left-hand side. And to do that, we have two terms that have a greatest common factor of 2x. So the method of factoring we're going to do is GCF. We can factor out a 2x. When we factor that out, we're going to be left with a 2x minus 1 equals to 0. And now we can go ahead and set each factor equal to 0 individually from the zero product principle. So we set the 2x factor equal to 0. We set the 2x minus 1 factor equal to 0. And now solve each one individually. For the first one, we can divide everything by 2. Divide by 2. We get x equals to 0. Over here, we would first add 1 to both sides. We get 2x equals 1. And then divide both sides by 2. We get x equals to a half. So we get two solutions. One is x equals to 0, and the other is x equals to a half. Let's take a look at the next one. In example 2, we're asked to solve 2x squared plus 7x equals to 4. It's another quadratic equation. This time it is not in standard form because we do not have 0 on the right-hand side, or at least on one side. So let's begin by subtracting 4 from both sides. That'll give us 2x squared plus 7x minus 4 equals to 0. Now that we have the left-hand side in standard form, we're going to try to factor this thing. It's a trinomial. So we should try to factor this. And if you recall from an earlier class, whether it be Math 101 or Math 102, to factor a trinomial, there's a lot of times two methods that are employed. There's the guess and check method, or there's also the more systematic AC method. Either way you slice it, this will factor. It's going to factor as a 2x and an x. We need a 1 and a 4, and then the signs are going to be a plus and a minus. So 2x squared plus 7x minus 4 factors as 2x minus 1 times x plus 4. Now that we have it factored, set equal to 0, we're going to set each factor equal to 0 individually. So we set 2x minus 1 equal to 0. We set x plus 4 equal to 0. And now we solve each one of those basic linear equations. We're going to add 1 to both sides. We get 2x equals to 1. Divide by 2. And so we get one solution is going to be x equals a half. Over here we subtract 4 from both sides. And we get our second solution is x equals to negative 4. Let's take a look at example 3. Again, it's a quadratic. We want to try to solve this with factoring. To do so, we want to get one side to be 0. So I'm going to make the right-hand side 0. And I'm going to do so by subtracting 6x from both sides and also adding 9 to both sides. Here's the equal sign. The 6x and the negative 6x will cancel. The negative 9 and the positive 9 will cancel, so we get 0 on the right-hand side. And now on the left-hand side, we're going to have three terms. They're not like terms. I'm going to write the x squared term first, then the x to the first power term next, and then we have our positive 9. So step 1, get one side to 0. The next thing we want to do is to factor the left-hand side. Once again, it's a trinomial. This is going to factor as x and x. If the last term is positive, then these signs have to be the same. Since the middle term is negative, that means that they're both going to be negatives. And then the factors of 9 that sum to 6 would be 3 and 3. We now go ahead and set each factor equal to 0 individually. And both of these linear factors actually produce the same value. They produce the value x equals to 3. So common theme we've kind of seen so far already is that these quadratics, these equations of degree 2, seem to almost always give us two solutions. Here we just get one unique real number, the value x equals to 3, but later on we'll come back to this. We'll say that this is actually a solution of order 2. Meaning that it's a solution that came up as a result of the factor x minus 3 being a repeated factor. But either way you slice it, the one unique real value x that solves this equation is x equals to 3. If we take a look at example 4, it almost looks like we can just go ahead and set each piece equal to 0, but we have an issue here, and that's that the right-hand side is equal to 6. And not 0. So before we can do anything, we're supposed first to clear off the right-hand side, get 0 on the right-hand side before we factor. So to begin, let's get rid of these parentheses and distribute. X times x is x squared. X times positive 3 is a positive 3x. Negative 2 times x is a negative 2x. And then a negative 2 times 3 would give us a negative 6 equals to positive 6. Combine these like terms, x squared plus x minus 6 equals to 6. Now we're going to get one side to be 0. We can simply subtract 6 from both sides. We get x squared plus x. Negative 6 minus 6 is negative 12. And then on the right hand side we have 0. We have one side to 0. It's in standard form. Now if we're able to, we want to try to factor this. The left-hand side does factor as x and x. We're going to have 1 plus and 1 minus. And it's going to be a positive 4 and a negative 3. Set each factor equal to 0. For the first one, we subtract 4 from both sides. So one solution will be x equals to negative 4. For this one here, you would add 3 to both sides. and we would get the solution x equals to 3. So standard way, oftentimes one of the easiest methods and approaches is if you can get one side to be 0, and if you can factor the other non-zero side, then we can simply set each factor equal to 0 via that zero product principle. Another way that's oftentimes easy to solve a quadratic equation is when the x to the first power term is missing. Then we can apply the square root property. For example, if you look at the quadratic equation, or just the simple equation, x squared equals to 9. We're looking for a real value, x, whose square is equal to 9. And essentially that's kind of like working backwards. The opposite of taking a square would be to do the square root. So if you take the square root of both sides of this equation, keeping in mind that any real number has two square roots, we have the principal root, which is the positive root, and the negative root. The square root of 9 is 3, and so we get two solutions. X equals positive 3, and x equals to negative 3. A lot of times you might see me write them using this plus minus notation. This means that x can be either the value negative 3, or x can be the value positive 3. Okay. So if you're able to isolate a perfect square on the left-hand side, the next step would be to take the square root of both sides, and that should allow us to solve for our variable. So again, the square root property says the following. If u is an algebraic expression and d is a non-zero real number, then if u squared is equal to d, we can solve for u by taking the square root of both sides. We take the square root of the left-hand side, we take the square root of the right-hand side, keeping in mind that we get a plus and a minus for the number. The square root and the square cancel, and we find that u is equal to the positive and the negative square root of d. Okay. It's important that whenever you want to apply the square root property, that you have to get the square term by itself first, and typically when we want to do this is when the x to the first power term is missing. Okay. Classic example of this would be number 5. We notice that there's 3x squared equals to 18. There is no x to the first power term. So let's begin by isolating the x squared. We can divide both sides by 3. The 3's cancel. We get x squared equals 18 divided by 3 is 6. And now to get the x by itself, we're going to take the square root of both sides. The square root and the square cancel because they're inverse operations. And on the right hand side, this will not break down at all. We get x equals the positive and the negative square root of 6. You can write it in either plus minus notation, or if you want to separate it out, we get x equals the negative square root of 6, and x equals the positive square root of 6. Take a look at example 6. We want to solve 2x squared minus 7 equals to 0. Again, the x to the first power term is missing. So we're going to begin by trying to isolate the x squared. We add 7 to both sides. We get 2x squared equals to 7. We can now divide both sides by 2. We get x squared equals 7 halves. And now from here we can solve by taking the square root of both sides. And don't forget, when you do the square root of the right hand side, it's a number. So we want to have that plus minus. The square root and the square cancel, so we get x equals plus or minus the square root of 7 halves. It's also possible to simplify this. So for some applications, some people say you're allowed to leave it like this. This is equivalent to, algebraically, the square root of 7 over the square root of 2, and then it might be possible to rationalize that denominator. What that would involve doing is multiplying the numerator and denominator by the square root of 2 to remove the square root from the denominator. We're going to get plus or minus. In the numerator, 7 times 2 is 14. So that's the square root of 14 over the square root of 4. And we know that the square root of 4 is simply 2. Okay. So either leaving it as plus or minus the square root of 7 halves, Or if you wanted to plug it in rationalized form, we could also give the answer x equals plus or minus the square root of 14 over 2. Let's take a look at number 7. Again, we're going to solve it the same way, so we're going to begin by subtracting 25 from both sides. We get 9x squared equals to negative 25. We can now divide both sides by 9. We get x squared equals to negative 25 over 9. So we've successfully isolated the x squared term. Now we can take the square root of both sides. We take the square root of the left-hand side. We take the square root of the right-hand side, which is a non-zero number. So we're going to go ahead and add our plus minus to that radical. The square root and the square cancel. So we get x equals. And now if we look at this, this is definitely going to simplify. Recall from the last section that if you have a negative under a square root, the first thing we want to do is break that out and separate that from the positive part, since that's going to be our imaginary unit I. And then we can evaluate the rest of the radical. The square root of negative 1 is I. And then this is one we can actually do. The square root of 25 ninths. It's the same thing as the square root of the numerator over the square root of the denominator. So it's going to give us 5/3. And then more commonly we would put the I term behind the real value part. So we get two solutions to this. They're both purely imaginary numbers. One solution is negative 5/3 I. The other solution would be x equals positive 5/3 I. Let's take a look at example 8. Here we want to solve x minus 1 squared equals to 5. This is one that, admittedly, we could try to solve it slightly differently. You could try to do something like what we did up here earlier, where you try and distribute the left-hand side, get one side to 0, and then factor. Unfortunately, doing so, this left-hand side would not factor ultimately. But what we can do is, if we notice, we have essentially a perfect square quantity equals to a number. So we can remove and get the x out of the square term by immediately doing the square root of both sides. So we can go ahead and take the square root of both sides. The square root and the square cancel, so we get the quantity x minus 1, and this is equal to plus and minus the square root of 5. And now from here we can simply add 1 to both sides. The 1's cancel, and we get x equals, we have a positive 1 with either a plus or minus square root of 5. So our solution in plus minus notation looks like this. X equals 1 plus or minus the square root of 5, or we can write it as two separate solutions. One solution is 1 minus the square root of 5. The other solution is x equals 1 plus the square root of 5. Okay. So either way would suffice. The next method of solving we're going to talk about is what's called completing the square. If we have a binomial expression, x squared plus bx, okay, then we can turn this into a perfect square trinomial if we add to this existing expression half of the coefficient of x squared. So this is the part of the process for completing the square. This is the kind of the magic number, if you will, that we really need. You take whatever the coefficient of x is. Okay, here it's the value b. What you want to do is take half of that. So you would first divide it by 2, and then you would square that answer. And that number will create a perfect square trinomial. When we add that b over 2 squared to our original expression, it will then factor as a perfect square trinomial x plus b divided by 2 squared. Where the thing on the inside, this might be a helpful tip, the thing that you're going to have on the inside of your perfect square is the part of the completing the squared number just before you do the squaring part. It's going to be the b divided by 2 number is what's going to go into here. Let's take a look at this. In example 9, it says what term should be added to each binomial so that it becomes a perfect square trinomial. So if I look at the first one, we have x squared plus 8x. So that value for b, if you will, is the number 8. What we need to do is we need to take half of it, and then we're going to square it. Half of 8 is 4. And then 4 squared will give us 16. So if we add 16 to this, it should give us a perfect square trinomial. Let's find out. So if I take x squared plus 8x, and we're now going to add 16 to it. Let's see how this will factor. Well, let's see. It's going to be x and x, plus and plus, and then factors of 16 to add to 8 are going to be 4 and 4. So sure enough, it does factor, and notice we get repeated factors. So we can write this simply as x plus 4 quantity squared. And again, you can see how that perfect square, that completely squared number, turned it into a perfect square trinomial. An easier way, once you add the 16s, we can go right to this last step. Again, notice the number that's going to be in the perfect square portion of this, the binomial part, is exactly whatever we had here the moment before we did the squaring part. So that's going to be your x, and then there should be a plus 4 on the inside. Let's take a look at part B. Same thing, we want to find the completing the squared number. So we identify the coefficient of the x. Coefficient of x is -7. We're going to take half of that number, and then we're going to square it. -7 is not evenly divisible by 2, so we just would leave it as -7 halves. And then when we square it, we're going to multiply it by itself. -7 over 2 divided by times -7 over 2 should be 49 over 4. So to complete and make a perfect square trinomial, we would need to add the completing the square number 49 over 4. With that number added, this thing will factor as a perfect square. It's going to be x, and then the thing that's going to go on the inside here, again, should be what you get right before you do the squaring. So it's going to be x minus 7 halves. We'll do one more. Here, to do the completing the square, we need to take half of 3/5 and then square it. To do half of 3/5, you're essentially dividing 3/5 by 2, which is the same thing as multiplying by the reciprocal. So we can do 3/5 times 1 over 2 squared. And that's going to give us 3/10 squared, which would be 9 over 100. So the number we would need to add this time to make a perfect square trinomial is going to be 9 over 100. This will then factor as x plus, right before we did the squaring we had the number 3/10 in there, so that should be 3/10. Let's now see how we can use completing the square to solve a quadratic equation. So let's see how we can use completing the square to solve quadratics. We can solve any quadratic equation by completing the square. If the coefficient of x squared term is 1, then we can add 1/2 of the coefficient of x to both sides of the equation. When we add a constant term to one side of the equation, we need to make sure that we add it to the same side of the other equation. Let's take a look at example 10. We're asked to solve by completing the square. First thing we want to do is we again want to kind of isolate the x terms on one side. So we want to get the x terms on one side. So what we're going to actually do is we're going to begin by subtracting 4 from both sides. So we begin by subtracting 4. That's going to give us x squared minus 6x equals to negative 4. The next thing we want to do is we're going to complete the square on the left-hand side. Again, to complete the square, we need to take half of the coefficient of x. So we're going to take half of negative 6, and then we're going to square that. Half of negative 6 is negative 3, and then negative 3 squared should be positive 9. So the completing the square number that we need to get a perfect square trinomial on the left-hand side is positive 9. We can add 9 to the left-hand side of the equation if we also add 9 to the right-hand side. The arithmetic on the left-hand side, negative 5 plus 9 is simply going to give us positive 5. Negative 4 plus 9 is positive 5. And on the left-hand side, this will factor as a perfect square. This will factor as x minus 3 quantity squared. And now, what we essentially have, because we completed the square, is we have a situation where we can use the square root property. We have a perfect square quantity equals to a number, so we can finish it off by taking the square root of both sides. We're going to get plus or minus the square root of 5. The square root and the square cancel. We get x minus 3 equals plus or minus the square root of 5. And then the last step to get x by itself is we're simply going to add 3 to both sides. The negative 3 and the positive 3 cancel, and we get x equals positive 3 plus or minus the square root of 5. Alternatively, if you wanted to split them apart, one solution is x equals 3 minus the square root of 5. The other solution would be x equals 3 plus the square root of 5. We can also solve this if the coefficient of the x squared isn't 1 by simply dividing every single term in the equation by that leading coefficient a. Let's take a look at example 11. Let's solve by completing the square. The first step is, again, we want to isolate the x terms on the left side. So we're going to add 4 to both sides. We would have 9x squared minus 6x equals to positive 4. We can't quite complete the square yet because we don't have a 1x squared. We now have a 9x squared. To get around that, we can divide every single term in the equation by 9. So we're dividing both sides of the equation by 9. When you divide a particular side by that number 9, you have to divide every single term on that side. 9 divided by 9 gives us 1, so we have a 1x squared. 6 divided by 9 is a fraction that will reduce to 2/3 x. And on the right-hand side, we have positive 4/9. We now have our x squared, 1x squared with a x term. So we're going to complete the square on the left-hand side. So we need to take half of the coefficient of x. So we need to take half of negative 2/3. And then we're going to square it. That is, we need to take negative 2/3. We're trying to divide it by 2. That's 2 over 1. To divide with fractions, we do keep, change, flip. Like this. Negative 2/3 times a half would give us negative 1/3. And then negative 1/3 squared would be positive 1/9. So the completing the square number we need is positive 1/9. So we can add 1/9 to the left-hand side if we also go ahead and add 1/9 to the right-hand side. With the addition of that completing the square number, we now get a perfect square trinomial on the left-hand side. It's going to be x with the number negative 1/3 on the inside. It's equal to, on the right-hand side, 4/9 plus 1/9 will give us 5/9. And now we can finish it off by doing the square root property. We're going to take the square root of the left-hand side. And the square root of the right-hand side. The square root and the square cancel, so we get x minus 1/3 equals plus or minus, we can write it as the square root of 5 over the square root of 9. The square root of 9 from that denominator is 3. So we get x, save it for a minute, x minus 1/3 equals plus or minus the square root of 5 over 3. And now to get the x by itself, we're going to add 1/3 to both sides. The 1/3s cancel. We get x equals 1/3 plus or minus the square root of 5 over 3. We already have a common denominator, so we can combine it into a single fraction if we like. 1 plus or minus the square root of 5, all divided by 3. If you like, we could write it as two separate solutions. One solution is 1 minus the square root of 5 over 3. The other solution is x equals 1 plus the square root of 5 over 3. Example 12 I'll leave up to you. It's again much more of the same. Just kind of go ahead and complete the square there. But one of the things that completing the square will allow us to do is we can actually apply this procedure to a quadratic in standard form. And ultimately what we get is what's called the quadratic formula. The beauty of the quadratic formula is if you have a quadratic equation in standard form, we have our ax squared plus bx plus c equals to 0. The solutions to this quadratic equation can be found by simply substituting the coefficients a, b, and c into this formula to get the solutions for x. Okay. This is a formula that you should absolutely memorize and put to use. It's a very powerful formula that you use quite a bit in both math and also in physical applications. The quadratic formula says that the solutions to the standard form quadratic equation are x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's use the quadratic formula to solve the next quadratic equation. It is ax squared plus 2x minus 1 equals to 0. Notice that it's already in standard form. The coefficient a is 8. B is going to be positive 2. And c is going to be negative 1. So first things first, identify those coefficients. Let's now go ahead and recopy down the quadratic formula. It's negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Next, we want to take our time nice and neatly, plug everything into the correct spots. X equals the negative of b, so that's negative 2, plus or minus the square root of 2 squared minus 4 times a times c, all divided by 2 times a. Next, we're going to use order of operations to simplify this. We have negative 2 plus or minus the square root. On the inside, 2 squared is 4. We have negative 4 times 8 would be negative 32. But then the negative 32 times negative 1 is going to make that a positive 32. All divided by 2 times 8, which is 16. We have x equals negative 2 plus or minus the square root of 4 plus 32 is 36, all divided by 16. And then lastly, we can simplify. The square root of 36 is going to be 6. So we get x equals negative 2 plus or minus 6 divided by 16. And from here, we definitely want to split this apart because we can simplify each of these calculations more. So one answer is going to be negative 2 minus 6 over 16. The other is x equals negative 2 plus 6 over 16. Negative 2 minus 6 is negative 8 over 16. Negative 2 plus 6 is going to be positive 4 over 16. And then we can reduce each of these fractions. Negative 18 divided by 16 divided by 8, top and bottom. That reduces to negative 1/2. And this one should reduce to positive 1/4. So we get two solutions to this quadratic equation. They are x equals negative 1/2 and x equals 1/4. Let's take a look at the next one. We want to solve again using the quadratic formula. 2x squared equals 4x plus 1. Before we can identify the coefficients, we need to put this thing in standard form. So let's begin by getting one side equal to 0. To do that, I'm going to subtract 4x from both sides of the equation. And I'm also going to subtract 1 from both sides. On the right hand side, the 4x and negative 4x cancel. The negative 1 and the positive 1 cancel. So we have 0 on the left hand side. So we have 0 on the right hand side. On the left hand side, we have three terms that are not like terms. We have a 2x squared. We have a negative 4x. And then we have a minus 1. Now it's in standard form. We can clearly see that a is equal to 2. B is equal to negative 4. And c is equal to negative 1. We're going to plug it into our quadratic formula. It's going to be x equals the opposite of b. So that's going to be the negative of negative 4. Plus or minus the square root of b squared. That's negative 4 squared. Minus 4 times a times c. And it's going to be all over 2 times a. From here, let's simplify. The opposite of negative 4 is positive 4. Plus or minus the square root of 4 squared is 16. Think of this as negative 4 times 2, which would be negative 8. But then a negative 8 times a negative 1 would give us a positive 8. All divided by 2 times 2, which is 4. We get x equals 4 plus or minus the square root of 24, all divided by 4. Notice that the square of 24, even though it's not a perfect square, it is divisible by the perfect square 4. You can write this as 4 times 6, where the square root of 4 is going to be 2. So the square root of 24 will reduce to 2 square roots of 6. And now that numerator will simplify because we have a common factor in the numerator of 2. We can factor the 2 out of the numerator and use it to cancel a factor of 2 with the denominator. So 2 goes into itself once, 2 goes into 4 twice, and so what we're left with is our final answer. We have x equals 2 plus or minus the square root of 6, all divided by 2. Which again, if you want to, you can write as two separate terms. So one root is x equals 2 plus the square root of 6 over 2. The other solution is x equals 2 minus the square root of 6 over 2. Let's take a look at the next one. Let's solve using the quadratic formula 3x squared plus 2 equals to negative 4x. Again, to apply the quadratic formula, we need to have it in standard form first. So we're going to go ahead and we're going to add 4x to both sides. Negative 4x and positive 4x cancel, so the right-hand side would be 0. We have 3 terms on the left-hand side that are not like, so we just list them in order. 3x squared, we have a positive 4x, and then a positive 2. It's in standard form, so I can identify A, B, and C. A is 3. B, which is the coefficient of the x, is 4. And C is going to be positive 2. We plug it into the quadratic formula. It's the opposite of B, so negative B. That's going to be negative 4 plus or minus the square root of B squared minus 4 times A times C, all divided by 2 times A. From here, we want to use order of operations to finish it off. We have negative 4 plus or minus the square root of 4 squared is 16 minus 4 times 3 is 12. Negative 12, that is. Negative 12 times 2 is going to be negative 24. So we are at negative 24 here. All divided by 2 times 3, which is 6. 16 minus 24 is going to be negative 8. So we have the square root of negative 8. And now from here, we definitely want to simplify this. The square root of negative 8. Once again, we have a negative under a radical. So we want to break out the negative square root of one part. That's going to be I times the square root of 8. The square root of negative 1 is I times the square root of 8 will break down. Perfect square of 4 divides into it. So we can write the square root of 8 as the square root of 4 times the square root of 2. And the square root of 4 we know is 2. So we get I times 2 square root of 2, which most often people will write it as 2I square root of 2. So we get x equals negative 4 plus or minus 2I radical 2, all divided by 6. And we can simplify this a little bit more. There's a common factor of 2 in the numerator, which we can factor out. That'll leave us with negative 2 plus or minus I squared of 2 all over 6. And then we can cancel the common factor of 2 in both top and bottom. So our final answer is going to be x equals negative 2 plus or minus I square root of 2 over 3. Can certainly leave it like this. If we wanted to, we could also split it apart. So for all intents and purposes, the way that we have the answer written, I would be perfectly fine with. When you go to do your homework in WebAssign, they might want you to enter it. This time we actually do get 2 complex solutions. And we know that anytime we have a complex number, that to be strictly speaking, we do want to write it as a plus bi. So what that would look like would be the following. We have one answer is going to be x equals negative 2 plus I square root of 2 over 3. The other answer is x equals negative 2 minus I square root of 2 over 3. And then, if need be, we can split apart the denominator here. Split apart the numerator. We have negative 2/3, plus we could write it as the square root of 2 over 3i. And then, in this form, it looks explicitly like a plus bi. Similarly, for the second solution, we can write it as negative 2/3, and then a minus. We would write this as the square root of 2 over 3 with the I to the right of it. Again, I'm fine if you leave it like this. I think this is nice and compact and easy. Notice that if WebAssign is asking you to write it in complex number form, that you may need to split each root apart and write it as a plus bi form. The last thing we're going to cover is what's called the discriminant in this section. The discriminant, where this comes from, is it's actually the portion of the quadratic formula that resides underneath the square root. And what the discriminant tells us is it tells us the nature of the roots that we get. So if you look at the portion of the quadratic formula, just the part that's under the square root, and for some reason my highlighter is not working, but this part right here, the expression b squared minus 4ac is what we call the discriminant. And the discriminant will tell us the nature of the roots. When the discriminant is positive, we get two real roots. If you were to graph the associated quadratic function, when you have a quadratic equation standard form, what you would see is that the graph of it would pass through the x-axis on two different occasions. So those two x-intercepts would be corresponding to the solutions of the equation. So we would get two real roots. If the discriminant is equal to 0, then we get one real root, which is sometimes called one real repeated solution. And if the discriminant is negative, if b squared minus 4ac is less than 0, then we get two imaginary roots. And visually what you would see is that the graph of the associated quadratic would either lie entirely above the x-axis or it would potentially lie entirely below, but it would never cross in that case. So if you're not necessarily concerned with the values of the roots, if you're only concerned with the actual qualitative types of them, you can use the discriminant. And in question 16, they simply ask us to determine the type of each number of solution. Here it's in standard form, so A is 3, B is 4, and C would be negative 5. The discriminant, let me call it D, is b squared minus 4 times a times c. So for this one, the discriminant is going to be 4 squared minus 4 times 3 times negative 5. 4 squared is 16. Negative 4 times 3 is negative 12. Negative 12 times negative 5 is a positive 60. And then 16 and 60 makes 76. And the value, we don't really care so much about the value. What we're concerned with is its sign. And because it's greater than 0, this means that this particular quadratic equation will have two real solutions. Let's look at the next one. It's already in standard form. A is 9. B is negative 6, and C is positive 1. So the discriminant, again, is going to be b squared minus 4 times a times c. If you forget it, just remember you absolutely have to know the quadratic formula. Just know that it's the portion under the square root in the quadratic formula. This is going to be negative 6 squared minus 4 times a times c. Negative 6 squared is 36. Negative 4 times 9 is negative 36. Times positive 1 will be a negative 36. And then 36 minus 36 is 0. Because the discriminant is 0, that means we will have one real repeated solution. Or you can just simply say one real solution. And then for the last one, do the same thing. Here, A is 3, B is negative 8, and C is positive 7. So we're going to do B squared minus 4 times A times C. Negative 8 squared is 64 minus 4 times 3 is 12, and then 12 times 7 would be a negative 84, and then 64 minus 84 is going to give us negative 20. It happens to be less than 0, so in this case we get two complex solutions. Not only do we get two complex solutions, but in general, whenever you get complex solutions, those two complex solutions will always be conjugates of each other. Because one will have the plus sign in between, The other one will have the negative sign in between.